95%. This is a reuse rate of 95%. We have 5% new water coming in, 95% recirculated water. We've added biofiltration. We've added some fine solids removal in this scenario. And we're looking at a 15% flow through the center drain here, 85% flow through the side box here. With this scenario, this flow rate actually exceeds our new water flow rate. So we'll have to recapture this flow here and send it back to the recirc loop. And then we'll have to discharge from these 3 or 4 primary locations to accumulate that 5% makeup water on the discharge side there. That's a good way to sort of manage that. In this scenario, we really want to try to get this number down because that will reduce the size of this settleable solids removal treatment center. The smaller the flow rate through there, the smaller the settling tank can be to remove those settleable solids. And if you take it one step further, even a purge system can utilize this technology quite well as well. Here we're looking at 10% new water coming in, 10% off the bottom center drain. You know, most of that water could probably be reused for production reuse, and then 90% taken directly back and exchanged for gas management, again, in that scenario. So it's a really flexible circular tank design technology that can be applied in a lot of different areas of aquaculture. Some details on inlet structures that I've seen done in the past. So this is a plan view of a circular tank. Obviously, these inlet structures are internal to the tank. And this is a profile view of these structures. One is really just constructed out of piping with slots or holes drilled in the pipe. The other one is an inlet structure that actually is removable on the inside of the tank and cleanable. And it has a series of orifices, inlet orifices or nozzles that allow you to adjust the flow and the rotation of the tank. Some inlet structures that are external to the tank. This is one, same concept, but the box is on the outside of the tank, and you have sort of these 2 different alternatives to flow direction in 2 different ways here. Again, this should be removable and cleanable on inside of there from the inside of the tank when it's empty. This one represents sort of a pipe that runs up out of the ground, and it has multiple little ports that go through the tank wall with adjustable nozzles just on the inside of the tank. I do like to have my inlet structure sort of external to the tank and keep the tank free and clear of most intrusions and things like that, so fish aren't running into them and things like that. And you can use relatively inexpensive equipment to accommodate this type of structure here. So bulkheads through the tank wall and these uniseal fittings to sort of do your junction with the tanks and things like that. This is an example of an inlet structure submittal that I did to just demonstrate how you would cut the appropriate slots in a pipe to achieve the right number of slots in open area to achieve our target water velocities. And then the bottom screens are usually custom designed. You really want to pay close attention to the fish size and the slot openings and make sure they're appropriate for the fish type and species and size as well. You'll often have a range of fish sizes in a tank, so you do have to size for the smallest size fish, but you also want to consider the larger fish and the flow rate associated with that. So, again, if you maintain that constant feed load across the whole growth cycle of the fish, then your flow rates through the center drain and your open area shouldn't have to change that much, but the whole size will need to change with the size of the fish. Tank lighting has become a really important feature on these tanks recently, especially for salmonids. It's become very apparent that lighting is very critical at certain stages of the life cycle for smoltification, and for feeding, constant feeding in some cases. So, you know, we've gleaned some technology from the pool industry for tank lighting, and there's some underwater lights available for culture tanks, especially deep tanks where you might get, you know, less light down at the bottom, higher light levels at the top. You might have some fish stratify, so just consistent light levels in tanks, really important. Some biomass estimators in tanks. So this is an example of a biomass estimator that can identify fish and the fish size and the total biomass in your tank to help you manage your tank's biomass. And then this sort of brings all the different features together in one or two different slides. But you know, covers over tanks to help manage lighting has become pretty important. If you consider the size of the tank, a lot of times these tanks will require individual covers and individual light cycles in each tank. Here's a center drain that's relatively complex, but it allows for, you know, constant solids removal through one path, but also the potential for more removal on here through an alternate path, and as well as the pump out of the whole tank and fish collection and sorting and management through an alternative path. This would require a screen at the bottom that could get moved up and down automatically, and some flow control to assist the flow in one direction or the other, depending on what you're trying to do. This shows the lighting options on the tank. So underwater lighting around the tank perimeter, surface lighting over the top, a center drain light as well could be, depending on the tank size, could be appropriate as well. And this shows the morph removal process. So if you pull the standpipe, it forces water up through here, and then the dead fish can get pulled out into the side box and collected. At that point, this requires not only a side box screen, but a weir wall in the side box, which maintains the water level at this water level over here. That creates the differential pressure to force that flow up into that side box. Some other considerations for light cycles are the angle of the light. Be a winter angle and a summer angle that can be changed, as well as a morning and a night angle in some cases. So there's some work being done in that area. As well as feed distribution. So a lot of times you'll bring feed in through the top center and have a little distributor there that'll spread feed out over the tank. So it's applicable to, you know, just about any tank size, any tank material, configuration. Some examples of modular fiber reinforced composites that are good tank options with liners potentially. They can keep costs down and improve your lead times. And then on larger tanks, there's quite a lot of concrete construction, form construction, tilt-up tanks, and you know, this is an example of the tanks at Salmon Evolution. In this case, the tank has actually become the building in these cases. So to service the tanks, you are inside the tank walls with internal raceways around the perimeter of the tank and access to the center of the tank. And there's no building around these tanks. These tanks become the building itself. So pretty impressive tank sizes there. And then there are some circular tanks. Nordic Aqua Farms utilizes something similar to what was spoken about earlier today, but trying to utilize some of the efficiencies of raceway design to control your biomass and manage fish populations. Veolia RAS 2020 also applied similar technology as well. And the big question is always whether or not